Alright, what's up? My name is Little Cokes, or Sean Little Cokes if you know me from the Discord or Reddit. Um, I'm going to be making a quick, basic modding tutorial. This is not designed for absolute beginners, this is designed more for people who already know what a memory address is and how to search for them, how to use a memory address engine to find specific memory addresses. This video is kind of the next step, so I'll be going over writing basic Gecko codes and a brief overview of how assembler code works, and how to kind of modify it to get the mods that you want. So again, this is not going to be, I wish I could tell you exactly how to mod, exactly how to do everything correctly, but realistically I can't. Plus, I'm kind of also a beginner at this as well. I only started a few months ago. This is more so a basic idea, just to give you, some basic information, and you can work from there. So, yeah, let's get started. I have a few examples over here we'll be going over. Again, these are kind of pre-set up for this video. I'm not going to spend the time using the memory engine searching for all of these memory addresses. I'm going to assume that you know how to do that, and for the purpose of this video that you already found whatever memory address you're looking for. I'm just going to be over writing Gecko codes and having a basic idea of how assembler code works. So first thing I'll go over, I guess I'll start going over some some resources here. So I'll try to link most of the stuff in the description just so it's easier for you guys, but for writing Gecko codes, we're going to be using the weird code, Gecko code type, the weird code type. There's a lot of options here. If you go ahead and look down this column, we have direct write, if codes, pointers, Gecko register. We have ASM codes. A lot of different options here. I'm going to be honest, I don't use most of these. Most of what I use is these writes over here. These if codes, these conditionals, they are very useful. And down here we have ASM, so these types of codes where you can put your own custom code into the game. So yeah, I'll just get right into some examples here. So first example I'm going to go over is a basic write. So I'll do, up here we got an 8-bit write and fill. That's the first example I'm going to go over. So here I am in a game of Mario Superstar Baseball. And what I found was, ahead of time, I found the memory address for player 1's stars, which is this guy. And the game's paused right now. But you can see over here, player 1 only has 3 stars. Now, if I wanted to make a code for unlimited stars, just so we can star swing and star pitch for days, have to not worry about it, how would you actually go about doing that? So let's go ahead and bring up, we got a memory tool. I love this thing, you need it. I'll try to link it if I can remember. So yeah, here we are, here we have the player stars. This memory address right here is player 1, which is set to 3. As we see, player 1 has 3 stars. Second one right here, this 04, this is player, the other player, in this case player 3, which has 4. So what if I want to write a code to make it unlimited? Well, in essence, you would just want to make this some number that's larger than 5. The max is FF, which is hex for 255. So, whoops, what did I just do? There we go. So if I were to go ahead and just write this to FF, using this memory engine, we can see that now I have all these stars here. And if I were to just, star pitch right now, I messed up. Alright, if I just star pitch now, we see my star count does not drop. Over here you can see that it went from 255 to 254. So it's practically unlimited. So now, okay, so we found the memory address. Now, how do we actually go about writing the code? Well, if we go back over here to this website, let me zoom in a bit so it's easier to see. There we go, much better. So this website, again, this is the code type that you're going to be using to write Gecko codes. So first of all, what type of values are we dealing with? Well, for player 1 stars, or and player 2 stars, it's only 2 digits, right? Before it was 03, right now it's FE, and player 2 is 04. So a 2-digit hex number is known as a byte, or you can think of it as 8 bits. A bit would be that refers to binary code, so 8-bit value would have 8 digits in binary. Simple as that. So we're going to want to use this guy, which is the 8-bit write and fill. And we can see in this little description here, writes the value XX, which is these last 2 digits right here, to Y. This is consecutive. Don't worry about that. Starting with the address at BA, which stands for base address, plus this underline. So, a lot of words there, but let's try to make some sense of it. So, I already have this code done ahead of time. Kind of makes life easy. Where are we? There we are. I have it turned off right now. Hoping you guys can see this. Well, I can't. Okay, there we go. We can zoom in. So here we have the code. This is for player 1 and 2. Bottom one's player 2. This one's player 1. So let's just focus on player 1 for now. So remember, our memory address was this guy. Let's zoom in again. This 8089286. That's player 1 stars. So what we're going to do, we're only going to look at these last 6 digits. Conveniently, in Gamecube code, in its memory, pretty much every single memory address is going to start with the same 2 digits, 80. In the case that it starts with 81, which is a possibility, all you have to do is just add 1 to this last digit here. And I'll explain that a bit more later on. It'll make sense. Don't worry. So we're only going to focus on these last 6 digits because, again, the first 2 are 99% of the time going to be 80. So since we're dealing with an 8-bit write and fill, we're going to replace those first 2 digits with 00. And the last 6 digits are going to be the memory address of interest. So this 8089286 becomes 0089286. So what this means is write an 8-bit value to the memory address 80899286. We're going to leave these first stitch, and then the second part here, we have a space. Sorry, I'm fumbling over my words a bit. We have 6 zeros, and then the last 2 digits are FF. And that's it. We have write to this memory address this 8-bit value of FF. And essentially, every frame of the game, it will give player 1 255 stars. And it'll constantly rewrite it every frame of the game. Unless you can somehow throw 255 star pitches in less than a frame, you're never going to run out of stars. And that's really it. It's a very simple code. The hardest part is just finding the memory address. But once you find the memory address, writing the Gecko code is very simple. If you haven't figured it out by now, I probably should have mentioned this before going over the Gecko codes. They all follow this basic format where it's 8 digits, a space, and then another 8 digits. The first part will pretty much always be some instruction at a specific memory address, and then the second part over here will be, what are you trying to do, right? So the instruction here is write an 8-bit value at this memory address. The second part is, well, what are you trying to do? Well, we're going to put this value, FF, this 8-bit value, at that memory address. We're going to write it there. And that's it. So very basic example, pretty easy code to write, in my opinion. Now we're going to get a little bit more advanced. So our second example is right here. And you can see I have it written down. This is the instruction for Yoshi's plant. So this memory address was necessary for the hazardless Yoshi's Park cheat code. So let's go ahead and copy this. We're going to switch over to Dolphin over here. Put that in. Pause the game and then put it in. And now we have some line of assembly. So this is the part of the video where I'm going to start getting into assembler code. So before I go over this, I'll try my best to give a brief, comprehensive guide and synopsis of assembler code. You're not going to become a ASM, coding wizard after my brief guide. This is, again, it's not supposed to be entirely comprehensive. I just want to give you an idea of what's exactly going on. How does the game actually work? Essentially, assembler code is, it's often described as the closest you can get to a human readable code that's also raw machine code. All assembler code, if I were to go ahead here, hit replace instruction, all assembler code is going to be an 8-digit hex number. And if you were to convert this hex number to binary, it would just be zeros and ones, which is raw machine code. So this is why, it's described as the closest you get to machine code. What assembler will do, in general, you're going to be moving numbers into these registers over here. We have R0 going to R31. These are registers. You have 32 registers for the Gamecube. All this other stuff, this F0, this stuff, we're just going to ignore that. Pretend it doesn't exist. Just look at the registers here, 0 to 31. Essentially what assembler does, you're going to be modifying these registers, using it to do math, move some data around, and that's as basic as an explanation as I can get before going too much in depth. But essentially, assembler code, you're doing math is essentially it. You're moving numbers and values to these registers here. So what we found for the Yoshi's Park hazard list cheat code is that the plants, when they spring up, they have a certain memory address. Each plant has its own memory address, and the value of that memory address changes based on whether the ball's close and if it's going to spring up and eat the ball or do whatever. But we ran into a problem. We tried making a cheat code where we would just write this memory address to always be 0 so it would never sprout, but it didn't work. And we realized that the memory address actually changes each time you load the game up. It's very strange. Sometimes that happens with how the game is compiled. But alas, we had to take a different approach. So instead, we just went right to the assembler code. And we said, okay, well, instead of changing the address of the plants, why don't we just change the instructions that are setting the value of that plants to whatever number? And that's the approach we took. So this is the code of interest right here. So we have this instruction right here, li r01. What this means, it says load immediate to the target register, register 0, a value of 1. So basically what this will do is you go to R0, register 0, it's going to set the value at register 0 to 1. And then a little bit down the line, we have this STB instruction. This means store byte at register 0 to the memory address at register 30 with an offset of C4. A lot of words there, but essentially what this code is doing is that we're saying, hey, listen, we're going to make register 0 equal to 1, and then we're going to store the byte at register 0, which is 1, to the memory address at register 30 plus C4. And this the memory address that it's storing to just so happens to be the plants of Yoshi's Park. And so what we did for this code is we just said, well, hey, it's storing at 1, and then that's what's changing the memory address and making this plant sprout. So why don't we go ahead and say, hey, let's replace this instruction and change it to 0. Now it's load immediate to register 0, a value of 0. And now it's going to store a value of 0 to the plant's memory address. And so in theory, this should make it so that the plant does not sprout. So I'm going to try to do that now while playing the game. Excuse if I'm not that good at playing. I'm playing on a keyboard and mouse here. But let's go ahead and charge. I'm going to strike out there. Alright, fair enough. Let's try again. No plants springing up there. Probably shouldn't have hit a home run. But no plants were springing up there. I'd probably, if this were actual testing, I'd do that a couple more times. But I know that it works, so I'm just going to ignore that. The plants don't spring up is essentially what I'm trying to get at. Because we changed the instruction that causes the plants to sprout in the first place. So in order to do that, how do we actually change the instruction? Well, I said earlier that these are 8-digit hex numbers. An 8-digit hex number is also known as 32 bits. So again, we're going to go back to this Gecko code type, and it becomes the prefix now, instead of being 00, is 04. Again, we have this base address there, and then the code that we want to add in. The code we want to add in, it's a bunch of numbers, and how do you know what numbers to use? Well, we're going to go over that real quick now. So this is ASMWiird, pretty much an essential tool. Absolutely need it. Makes your life so much easier, modding. It does a lot of work for you. So this is the address we want of interest we want to look at. And we said we wanted to change it to this. So let's say I didn't, I already knew ahead of time that I needed to change it, that last digit in the code. Let's go to replace instruction. I already knew that I needed to change this number to 0. But let's say I didn't know that. How would I find that out? Well, here we have the instruction here. Let's go ahead and copy the code line and paste it into there. There's our instruction. And so I want to change it from load immediate 1 to 0. So all I'm going to do is just change that to 0. We're going to hit convert, and we're going to ignore these top 2 lines for now. We'll get to that later. This line right here, 38 followed by 6 zeros. Let's copy that. Replace instruction, paste. And there we go. That's exactly what we wanted. So, in order to put this in the Gecko code, let's go ahead and take a look at some Gecko codes right now. Hazlitt's Yoshi's Park. There it is. 04. So, write a 32-bit value at this memory address. Whoops. Okay. There we go. This memory address, which is the guy over here. 38 followed by 6 zeros. And so you can actually use these writing values to directly change game code. Directly change some instructions in assembly by just using this 04 prefix. So awesome. Now you may have noticed, if you got a sharp eye, there's some other stuff here. We got this top line, we got this bottom line. What the heck's all that? That leads us into the next step, which is conditionals. So I mentioned before, these are incredibly useful. Here we have if equal, if not equal to, if greater than, blah, blah, blah. These are conditionals. Essentially what they do is that it won't execute the code below it until a certain condition is met. So for this prefix 20, it will execute the code below it if the address specified here is equal to these values. If it's equal, then it'll execute the remaining code. So the reason why I had to put in conditional here is because we noticed a weird bug with Yoshi's Park in that it caused glitches outside of games. The menu became janky, and overall sometimes the game would just crash. It worked fine in-game, but out of game, on the main menu and stuff like that, it caused bugs. So what we did is that, okay, we're just going to set a conditional so that way the code's only active when you're in a game. And so that's what this does. So it says if this memory address here is equal to this value, all I did was find some line assembly that is equal to a specific value when you're in a game. So this is like the indicator that we are in a game. If it's equal to that number, then execute this code. This last line is essential because it ends the if statement. If this wasn't here, it would apply the conditional to all the code below it. This line right here ends the conditional. And so that way this conditional, if equal to, will not apply to code below it. So in conditionals can be a lot more fun. I have another code over here. I have it called auto dingers. And this one's also a lot of fun. So let me zoom in again. What this one says is that this one is actually 28, not 20. 28 is simply, there we go, 16 bits. So not 32 bits, but only 16 bits, which is a 4-digit hex number. What this one says, this actually looks at player 1's button inputs. This memory address right here is some player 1 memory, player 1's button inputs. So what this does is that basically, again, these first four digits are irrelevant. If we look at this code, these M's are, a little bit weird stuff. We're just going to set them equal to 0, not worry about it. We're only concerned with these last 4 digits here. What this says is that if this memory address, 16 bits, is equal to 0110, This first 0, 1 correlates to player 1 pressing the A button, and the second one correlates to player 1 pressing the Z button. So, if this is true, if player 1 is holding down A and Z, it will execute the remaining code right here. And of course, we have an end conditional statement right here. So, what does this stuff do? These are, again, basic writes, 8-bit writes right here. And what this actually is, you might have been able to read here, auto dingers. This will pretty much max out your batting stat. If we go, here's the table of memory addresses that we have. Incredibly useful. Let me see if I can zoom in. I can't. Oh well. Here we have batting, contact hitting power, charge power, and the contact spot. Essentially, if you hold down A and Z at the same time, your batting stats become maxed out. As we see here, this one, this 9-0 guy, that's the charge power of the batter, and the 9-1 is the contact hit power. So I have this turned on so we can actually go ahead and see this in real time. So let's do that now. So I'm the batter right now. I'm also the pitcher, but we're just gonna focus on the batter. So I'm gonna hold down A and Z. Let's go hold it down. There we go. And then I'm just gonna crush the ball out of the park, and that thing is gone. It's going to the parking lot. It's pretty much an automatic home run there. So that one's a lot of fun. If both conditions are met, it changes it. So you see during the replay here, actually, I'm not holding down the buttons. Let's see if the ball lands somewhere else. No, it didn't. All right, whatever. Essentially, that code is going to let you just absolutely crush the ball. Once those two conditions are met, you're holding down A and Z, you will absolutely crush the ball. So moving on. So that was conditionals and basic writes. The last part is assembly injection code. This is where ASMWiird is just incredibly useful. So I have something prepared here. This is 8, what is this guy? Let's see. -2 stars for captain. So it's kind of annoying in this game. If you use a star swing on a captain player, that's not actually your captain. So for example, in this game, player 3 here is is Luigi captain, but Birdo is a captain player, but not actually the captain of this team. If you use a star swing with someone like that, it's actually -2 stars instead of -1. And not everyone likes that. It kind of sucks. Makes the character a lot less useful. So we went ahead and made a code where it's always -1 star for those captain's characters instead. So I have it turned off right now. Again, this is something that I'm assuming you already found this memory address. Let's go ahead and plug this guy in here. And here's the instruction right here. It says sub these, whatever. So let me actually set a breakpoint here. So that way we can get a look at the registers at that point in the game. So let me go ahead and hold down R, and let's go ahead and use this star swing. There we go. The game pauses because because we hit this breakpoint. So SUB sub R0 R7. What this code means is that this says subtract the value at register 0 and register 7 and store the result at register 0. So we see register 0 right now set to 5, which is player 3's star count. Register 7 is set to 2, which means it's going to subtract 2 stars. And then store the result at register 0 right here. So, let me go ahead and... Where is register... where is the stars? There we go. Player 1. Let's go ahead and look at player 2 right now. There we go. So 5 stars right now. Oh, whoops. 5 stars right now, as you see right here. And if we execute this code, it should drop down to 3. There we go. 3. Now it's set to 3. If we go ahead and look, there it is. Register 0 is equal to 3. And if I were to continue the game, I should have only 3 stars left for player 3 here. Now I gotta end the inning. There we go. And let's go ahead and look. Yep, 3 stars left. That's kind of annoying, right? We lost 2 stars, and so how do you make it so it only lose 1 star? So let's go ahead and look at the code for that. So we have star string is always minus 1 star. We got this guy. This C2 prefix is, let's go down here. Where is it? Let's find it real quick. Yeah, there we go. Insert assembly. C2, blah, blah, blah. So this is where this program comes in handy. It writes the injection code for you. And that's what this C2, this stuff up here means. So we said we want to look at this address right here. Let's go ahead and plug that in. And then the assembler code. Well, remember in the code it said it was going to subtract, the register 0 and registers 7. So let's go ahead and look at that again. So let's pause the game. Go ahead and look here. So we see here it's going to subtract these values and then store the result at this memory address in register 5. So let's go ahead and copy these code lines. Let me see real quick. Yep. So let's copy. Sorry, it's being buggy right now. Let's go ahead and copy this code line, paste it there, and then we're actually going to need a second one as well. So let's go ahead and copy this code line, paste it there. So what we want to actually do, oh sorry, we don't need this, never mind. What we want to do is make it sideways subtracting only 1 star instead of 2. So let's go ahead and look at the code. Let's see how we did that. Whoops, where were we? There we are. Sorry, my brain just stopped working for a second. Please excuse me. Let's go. Oh man, that brain is not working. What was this guy? Alright, this guy does not want to work. There we go. Never mind, my brain stopped working. Okay, never mind. So, we want to make it so that way it's subtracting 1 instead of 2. Well, remember register 7 was set to 2. So what we're going to do to go around the problem is we're actually just going to set register 7 to 1. So li load immediate register 7 1, and then the second code line is going to be this exact guy. We still want to subtract the 2 numbers. Keep in mind that if you do insert assembly at a memory address, it will replace the instruction at that address. So if you want to add something, you're going to have to include that original instruction in your code over here. Because again, we're replacing the instruction at this memory address. If I were to just put this li r7, I would be getting rid of the subtracting function, and we'd start seeing some bugs. So what we're doing here is that we are setting register 7 to 1, and then we're subtracting the stars for player 1 by 1 and storing it to register 7. So if we go here and create the code, we get this guy, and that just so happens to be exactly what we have over here. So that's where assembler ASM injection comes into play. It becomes very useful because now we can actually start to change some functionality of the game. The last example I'm gonna give, you can see I ran out here. This is actually a fun one. So this code, all duplicate characters, really annoying. This one took forever. We kind of figured it out pretty quickly, but the bugs just start piling up and took a lot of time. So you see it's a very long code, but it kind of uses almost everything we've gone over in this video in this code. So let's break it up into parts here. This first, let's go over this part actually. This whole chunk right here, this is again just writing values, 0, 4 to whatever. I could have done this actually by using 0, 0 instead to write 8-bit values, but since they're all next to each other, since all the addresses of interest were next to each other, it just saves space to use 0, 4 instead. But basically, what this chunk of code does it looks at the memory addresses for whether a character has been selected or not. So all these 0 guys. It's set to 0 when a character has not been selected, and 1 to when a character has been selected. They're all 8-bit values, and I want them always set to 0, so that way you can just keep clicking on characters. This bottom part with the FF actually has to do with the icon that shows up, the image, how it's blacked out when you selected someone, and you can see their image when you can select them. This has to do with that part. Like I said, these are all actually bytes. 8-bit values. Yeah, bytes. I was right. It just saves space in the code. I could have done 0, 0, this memory address, and then went on to the next one. But it just, since they're all next to each other, it just saves space to use 0, 4 instead. So this part of the code is just straight up writing memory addresses, writing these byte values. This upper part here is some code injection, ASM injection. This 6 followed by 7 zeros, actually stands for NOP, or no parameter. Basically what this means is do nothing. If you were to insert a NOP, that just means, that tells the game, just do nothing here, continue on. It's effectively just removing that line of code from the game. These NOPs here refer to the random button, so that way you can get multiple characters picked on the random button, and the character variants, the ones with different colors. It allows you to pick any variant as many times as you want, because the variants actually gave some bugs in the game. We had to go ahead and fix that with these NOPs. So these are changing instructions in assembly. And then this last part here, C2, this is ASM injection, the last thing we went over. So if I were to, let me pull it up. There we go, attempt to fix rando glitch. This is the actual assembly code, the assembler code that I use to actually fix the glitch. So again, this is where ASM injection becomes really handy, and this is where the ASMWiird tool becomes really handy. Essentially what this code does in a nutshell, there's a glitch with the random code where if you, with the duplicate code, where if you selected the random button, the game would sometimes select the captain again, and when it did that, it would freak out. Because it would realize that, hey, I'm not supposed to be picking the captain, and it would soft lock the game in some instances. So the way I worked around that is that when you press the random button, it briefly sets the captain as a picked character. And then after the random button's finished going through its stuff, then it resets it back to a pickable character. And that pretty much stopped the glitch from happening. So I wanted to put this code into the game. I found a memory address and instruction where I could put it in, and I went ahead and injected it right into the game. That's what this last part of the code is. This is the random button glitch fix. So I think that just about does it. That's kind of everything I wanted to go over. I actually just realized earlier with the auto home runs code, I actually did it wrong because I'm batting with player 3, and the code is for player 1. So let me go ahead and actually, for this last part of the video, let me actually show off the real code. Let me just wrap up the inning here. Oh, whoops. Hold still. Okay, let's just wrap up the inning here. Let me actually show off that code because I realized before that I did it wrong. It's now I'm player 1. I'm going to be just crushing the ball here. So again, I'm going to hold down Z and A. Let's wind it up, and now you can see the ball get absolutely crushed. That is max power. So that's how the code's actually supposed to work. I realized I messed it up earlier because I didn't have it turned up player 3. Now if you notice during the replay, I don't hold down A and Z. The ball actually doesn't go the same spot. It went a little bit shorter. I don't know if it was very easy to see. And again, it works for contact hitting. So this should, oh, yeah, you can see there's a little bit more power there. Waluigi's got a weird contact swing, but you can see the contact swing has a little bit more power. Oh, Mario's a good example here. Contact swing, and it just absolutely line drives. That would have been a home run, a contact hitting home run, if I hit the ball straight. Let's try it again. Yeah, I went contact there, and it was a home run. So that's actually the code working there. Sorry for messing that up before. But now you can see it working. And here in the replay, I'm not holding down A and Z, and you can see it doesn't work. So you have to hold down A and Z during the replay as well. So yeah, there you go. That's kind of everything I wanted to go over. If you want more resources on what these assembly instructions mean, I'm going to link another tool in the description. Here it is. This is a very nice PDF document. Goes over PowerPC assembly instructions, which is what the Gamecube uses. So if I were to scroll towards the bottom, let me see if I find it. Yeah, there we go. So for example, if I want to know how, I don't know, let's find something, STW, store word. If I want to know how that worked, I'll go through here. Let's see if I can find it. It's not here. It's probably because it's a common thing. Take my word for it. Just take my word for it. You can find a lot of assembly, how the instructions work on this. Some of them are specific to Gamecube. Some of them are common. So STW is a bad example. So if I were to just Google the STW instruction, not stew, STW instruction ASM, I should find, there it is. I should find a basic example of how it works. There we go, STW, and this is going to go over how that works. This is more for specific instructions to the Gamecube. Sometimes you can't find it online, so I'll try to link this as well. I think that's pretty much everything I want to go over. I gave some examples. Again, I'm assuming you know how to find memory addresses, but this is kind of just to give you a basic guide to writing Gecko codes, how all that works. So we can go ahead and make some cheats on your own. So yeah, that's about it. Questions, go ahead and leave that in the comments. Otherwise, I'm done. I got nothing else. Bye.